Once upon a time, more than 4.5 billion years ago, there was an unnamed planet circling an unnamed star. Its surface was molten lava, and it had no life upon it. Most of the big rocks that had come crashing together in a series of literal world-shaking events had been collected. They stopped crashing into this planet for a very long time. It began to cool and form a solid surface. Then about 3.9 billion years ago, it experienced another wave of collisions, which we have named the Late Heavy Bombardment. If you haven't guessed, that planet's name would eventually become Earth. This wasn't some trivial meteor shower, however. It was a continual barrage of thousands of objects per day, and not just rocks, but cometary bodies. So we got a lot of water and other useful elements like nitrogen. Aside from the oxygen that was bound up in the water, there wasn't much of it around in the environment. Our early atmosphere would have been completely toxic to most current forms of life on our planet. Nevertheless, some chemical process started to take hold and to create little collections of chemicals that were enhanced by the presence of other substances. These substances weren't required, but made it more efficient. Those were called catalysts. Chemistry can be thought of as a crowd of people that each want to tie a shoe, but they're only allowed to do it one at a time while standing on one foot and holding the other shoe up in the air close enough to reach it with their hands. It's awkward, slow, and that idea is fairly representative of chemical processes. Give that same crowd a chair, and suddenly the process of shoe tying becomes incredibly quick. The chair itself isn't changed by helping these other reactions and can be used over and over again. The chair provides an ideal surface for the action to take place. When chemicals find ideal situations to react, they clump together, making more complex molecules. In the presence of ultraviolet radiation from the sun, providing a good deal of energy, they can also accomplish these reactions much more quickly. Almost everything that speeds up the reaction is considered an advantage, and so they come together in even larger collections. Some other reactions happening nearby might be detrimental, growing a layer of inert, unreactive, or waste product on the outside of the chemicals, which wouldn't react with the neighboring chemicals, protected the reaction and allowed it to continue efficiently. This was how the first cell walls evolved. This process continued until simple viruses evolved. They were really chemical packets with a cell wall that weren't alive. They would take in light energy and make sugars out of carbon and hydrogen, known as carbohydrates, so they could function. As they grew more complex, they developed a nucleus that controlled the cell, regulating how all the chemical actions in the cell progressed. Just as the brain is to the human body, the nucleus is to the cell. Now we can finally say that they were alive. These ocean-dwelling cyanobacteria created our oxygen-rich atmosphere by releasing oxygen as a waste product. Once there was plenty of oxygen about, many chemical reactions could take place much more efficiently, and more complex organisms evolved. Cells that complemented each other would make waste products that the other cells could use as a part of their own processes. Except for single-celled animals, everything that is currently alive is a collection of cells that cooperate. What you believe often depends on where you live and what your ancestors believed, and then what they told you was true. There is a tendency called hubris or vanity among human beings to believe that life here began here. It's easy to imagine a little pool of slime sitting somewhere on our planet with precisely the correct collection of chemicals, precisely the correct amount of interstellar radiation and ultraviolet light, a nearby lightning strike for extra energy, and all sorts of other coincidences necessary for the evolution of life. We have in fact replicated the beginning conditions for life, recreating the environment that existed on Earth at the time. This resulted in the creation of early protochemicals such as RNA or ribonucleic acid, which is needed before DNA or deoxyribonucleic acid can exist, which is the blueprint for every living thing on Earth. Interestingly, there is a good possibility that we are wrong. Down in the Antarctic, where the environment is pristine, clean, and white as can be, it's easy to find meteorites sitting right out in the open. We have found hundreds upon hundreds of meteorites that are clearly identified as having originated on the Moon and on the planet Mars. How did rocks from a completely different space body get to Earth? When a high-speed meteorite crashes into the surface of a planet, particularly a small one, with low gravity and little atmosphere, it's fairly easy to launch fragments into the sky. They can circle in the solar system for millions of years and eventually make their way to Earth. It is possible to identify them because we can tell through spectral analysis what the composition of the surfaces of the Moon and Mars are. They're unique signatures that inform us what they are made out of. The composition of the lunar surface was confirmed, of course, when the Apollo landers picked up collections of rock and brought them back to Earth in the 1960s and 1970s so we could examine their chemistry. The composition of Mars's rocks and soil has been confirmed by the numerous robots we have wandering its surface doing geophysical examinations. There are also a number of satellites circling that planet, studying it in more detail than ever before. Mars may have had life long before Earth ever did. The planet Mars being smaller and further from the sun would have cooled more quickly, and there is clear evidence that there was plenty of water on that planet billions of years ago. Before it cooled completely, it had a magnetic field like the Earth, which would have protected its atmosphere for millions of years. During that time, there is a distinct possibility that life could have arisen. Granted, it would have been a very simple form of life, but we know that viruses and bacteria are hardy enough to travel through space in a state of super hibernation, where all body functions shut down completely until the cell encounters water again, whereupon it resumes its interrupted activity. Trapped within a rock that was ejected into space, it could very well have made the journey from Mars to an otherwise sterile Earth, and being the cause of all life on this planet. In other words, we might all be Martians. When humans eventually travel to Mars, we might not be visiting a new planet. We might simply be going home. Yet, we may still be wrong. Perhaps life did not evolve on Mars either. Another theory suggests that the giant clouds of bioactive material that have been detected in space are the source of all life. It is called panspermia, meaning that the seeds of life are generated in free space, spread everywhere, and when they land on hospitable planets, off they go. The basic blueprint of life might be surprisingly consistent throughout the galaxy, or possibly the universe. If there is something we can take away from all this, it might be something that the famed astronomer Carl Sagan once said: "We are all made of star stuff." Literal elements that were created in the hearts of dying stars, and then exploded into the universe when they died. Now we can imagine that maybe, just maybe, life itself evolved between the stars, waiting for planets to form so it could express itself. If you have a philosophical turn of mind, you might consider the possibility that the universe invented life so that it would may have some way to understand itself and why it exists.